Good morning to all. In today's video, we will see pumping lemma theorem for regular language. The theorem says that it states that suppose L is a regular language recognized by a finite automata FA with with n states then for any string x belongs to L, where L is the regular language, with length of x, that is mod of x, it must be greater than or equal to n. X may be written as x is equal to UVW. In three parts we will divide that string. For some string UVW, now we will divide the string into three parts such that U, V and W satisfying two conditions. Mod of UV, it must be less than or equal to n, and mod of V middle part, it must be greater than 0. Then for any I greater than 0, U V raised to power I W, every string generated by this format, it must be belongs to L. So this is the statement of theorem. This n, this is nothing but the n states. It is called as a, this is known as pumping lemma constant. Then how to give the proof for this one? In examination, theorem can be asked only there for 2 marks, and theorem and proof can be asked there for 6 to 8 marks completely. Okay. Now here at the initially we will assume that the language is a regular language. Let L be a regular language. If it is a regular language, definitely there exists some sort of a finite automata which accepts this language L. Okay. Therefore there exists an automata we know definition of automata. M is equal to Q sigma delta Q0 F accepting L, that is L is equal to language generated by M, means given language and language produced by this M accepted by language accepted by this finite automata M, both are same. Okay, so that is L is equal to language, this is the notation. And what is the meaning of this one? That is nothing but the language accepted by finite automata M, accepted by f of a. And if L of G is there, G nothing but the grammar, that is nothing but the language produced by grammar G, that is L of G, and L of M is nothing but the language accepted by FA. Then we will assume here few things. Let n be finite automata is there, so there will be the some states, that is nothing but the q. Let's consider n be the number of states, of m given automata. Then second case, we need to consider one string from the language set L. Consider a string as A1, A2, A3 up to AM greater than this one. Okay, now this is characters of the string AM, A2, A3 up to AM. That is nothing but the length of string will be M, where M is greater than or equal to n. This is the first condition. We have to select the string where it is whose length is greater than or equal to n. That is the number of states. That is length of string greater than or equal to number of states of FA. Then third thing, see, we consider the number of states, then we have considered the string having length greater than or equal to number of states. Then third, the path for this string is starting in string is processed in a processing of string starts from the starting state, that is q0, and ends in state, final state ends in suppose qf, okay, where qf belongs to capital F. Okay, so any string we know that if it is a valid, then its processing starts at q0 initial state and ends in any one of the final state belongs to F. Okay, it is shown in following figure. A. Okay, let's see how it works for the finite automata. See, we know that there are the different type of the